Hello, my name is Nathan Deinlein, and today I'm going to be talking about Q function, which is an aspect of reinforced learning. So I thought I would start with a quote of Socrates saying, "All I know is that I know nothing." And that's really what we're starting here with a tabula rasa of an algorithm that knows nothing about its environment. And then it's going to build up its knowledge in order to be able to first explore its environment, but then eventually exploit its environment. So the agenda is very simple. First, we're going to talk about what the Q function is and what is reinforcement learning. Next, we're going to go into the mathematics behind it. How does the entire thing kind of work out mathematically? And then finally, we're going to look at a couple of different applications of how you could go about using this sort of learning. So what is reinforcement learning, and specifically the Q function? So it's an attempt to recreate the natural process of learning that we see in psychology with animals or humans. So everybody always remembers Pavlov with his dogs of if you ring a bell, the dog salivates. That's what's called classical conditioning, which is not actually what we're trying to create here. Instead, what we're trying to do is what's called operant conditioning, or recreating the environment of a Skinner box, which is not as terrible as it sounds. It's named after a psychologist named B.F. Skinner, who used the Skinner box to train pigeons to push a button under certain conditions, and that would give the pigeon a reward of food or water. So mathematically, what Q function and reinforcement learning is trying to do is mathematically figure out a series of rewards and the actions that cause them, and then figure out the state or the time elements that are involved with those. So let's set the stage a little bit. The first thing that we need to know is what are the rules of the world we want our actor to exist in. So when we drop this Q function into an environment, what are the rules of the world? Are there barriers? Are there pieces or penalties that we don't want the operator to accomplish? And we're going to do this through three simple pieces: the state, the action, and the reward. And the reward is quite possibly the most important piece because that's going to be how you go about training the actor. So the math behind this is very simple. It's based on hidden Markov models, and I'm not going to go through the math for those. That's a presentation all to itself. But the basic equation that you need to understand for this is that at state at any given time, if you perform an action from that state at the same time, you will get a reward in the next state. Now, whether that's a penalty, positive or negative, not important. All we're saying is that for a given state with a given action, we should get a reward in the next time period. If you understand this basic piece, you'll be able to understand most of Q learning and how it goes about doing what it does with reinforcement learning. So, what is the goal of the Q function? The goal of the Q function is to create a policy, and this policy is going to dictate future actions. So how do we go about acting in our environment? Think of it as taking the knowledge of how to walk and applying that to the knowledge of how to run, and it's going to optimize it on the Bellman equation, which I'm going to talk about here in a second. But very simply, what we're trying to do here in the Q function is that for a state and an action, what is the expected discount cumulative reward? So if I stack up all of the rewards by going down this path, what is going to be the maximum reward that I can accomplish by following this policy of going down a certain set of states and actions to achieve these certain rewards? So that's what this equation is basically showing here. And then once we have this, we get what's called a policy. So let's look at the Bellman equation really quick, because this is how we go about optimizing Q function. And it basically states that at any state in action, so S comma A, the reward after taking that action, remember that RT plus 1, should be the maximum gratification that we can get by going down that policy. So what is the optimum of leaving that space, going to another space, and getting that reward? That's what this mathematical equation is saying. And because of how Q learning works, it's often used on games. It's very, very popular to use on games because in any game, it perfectly creates an environment of hidden Markov models where there is a set number of states and a set number of actions that can be taken at any point. And so we can run through every single possible combination of all of those in a way that has definite rewards. So it's very popular to use this type of learning and test it out on different types of games. So in order to start setting all of this up, we need to create what's called a Q table. And what a Q table is a simple grid combining all of the actions and all of the states so that we have the first part of our equation, that S comma A. Now, the most common example is shown using a simple board game. We have a simple piece. It can go in the 4 cardinal directions, and each square is considered a different state. Each move on the board is a different action. And I'm going to kind of walk through that example, but understand that there is a real-world example of, let's say, a self-driving car where there's obvious actions and states that can be taken, and there are obvious rewards and punishment, i.e. getting to your location and not hitting pedestrians along the way. So now we're going to start walking through this basic game example. So I'm going to create a game where you're trying to hike. This is a real world example. If I am a hiker in space number 5 right there, I want the algorithm to punish me for going off the trail because I'm destroying nature or I'm going a harder way than I need to. So I want it to punish me for going off the trail. So what I've set up in the top left corner is a series of rewards. So obviously I want to be going towards square 9 because my reward there is 100 points. I don't necessarily want to be going in any other direction. I don't want to be going backwards, say, because that'll put me in the parking lot and risk me getting hit. So we're going to put negative 100 points there for going off of the trail. Now that I've got this set up of, I have the states and I have the actions that I can take and I have the rewards for those actions, I can start setting up my Q table. So if you look to the right, you can see every single action that I can take, forward, back, left, and right, and then the states, in this case the names of the squares that can be found in the bottom right corner, 1 through 9. So now that I've got all of this, my actor knows absolutely nothing about the environment to start with. So we're just going to fill in our Q table to start with a whole bunch of zeros because we don't know anything yet, so we can't create Q values for what a given action and state will do for reward. We're going to get to that here right now. So at the very bottom, you'll see our exact same setup that we had, except for now I've got a value in the Q table. So how did I get that Q value? And what we're going to do right now is just we're going to set the learning rate and the discount rate to 1. I'll explain what those are in a second. But we're going to walk through the math behind this. So our current Q values, if I'm standing in square 5, is 0. I didn't have any prior knowledge of what the points, what the reward would be for just standing in the spot. So we're going to put in 0 for that first piece. The next part is if I move forward then, we're gonna go forward to square 8. What would my reward be if I move to square 8? And that's -1. The next part is the maximum expected future return. What does that mean? If I look at my Q table and look all around at every possible action that I can take moving from state 5, in our first table, they're all 0 because we have no knowledge. So we're just going to fill in 0 for that. But as we start to fill out the table, we can look at, all right, from 5, if I move towards 8, the Q value for that is going to be different than if I move to the right and move into square 6 or state 6. So you can see how this table will start to build out. And then the final piece is just to drop in our current Q values again, which is going to be 0. When I multiply and add all of this stuff together with our learning rate and our discount rate, I get that my new Q value should be -1. So I'm going to go in and I'm going to update my table to say that at state 5, if I move forward, my new Q value will be -1. Now that I've got this information, I'm going to turn the algorithm loose to just do this over and over and over again and figure out what the maximum should be for moving from space 5. In this case, it will be to move forward because it has the least penalty from all of those. But moving forward, or moving to the right from, say, square 8 is going to give me 100 points. So when we go back to our policy and looking at, all right, we want to maximize our future rewards, eventually the algorithm is going to say, yes, go from square 5 to square 8 to square 9, because that'll give you 99 points, versus going from square 5 to square 6 to square 9, which will only give you 90 points. It's going to try to maximize those future rewards using the Bellman equation to do all of that. So this is a very not helpful understanding of how this works, because very clearly I'm trying to push the algorithm in a certain direction with my rewards. We're basically Hansel and Greteling this of leaving a whole bunch of stuff behind it. That's not really what reinforcement learning is used for. If I know definitely this is the correct way that we should be going and this is the correct action that should be taken, probably better ways to go about doing this that are less computationally heavy. But let's look at a real-world application of this. Staying on our idea of hiking, if I give the algorithm a topographical map and say, I want to go to the top of Hill A, find me the fastest, easiest way to get up to Hill A. What we can do then is create a series of very complex reward values for each of the different states that we find ourselves in. So if you go up a hill, obviously that's going to take more effort, so we're going to put a negative penalty for that. If we're going downhill, we're going to put a positive penalty because it's a little, or a positive reinforcement because it's a little bit easier, but we're probably not going up a hill then, so it's maybe not the easiest. We might put in pieces for penalties for long distances or avalanche conditions. There are a number of ways to go about figuring out a very complex reward system for this map. And then when we turn our algorithm loose on this, what it's going to do is it's going to create a policy to go through and figure out what is the easiest way to get up to the top of Hill A in our map, basing it off of, all right, what's the minimum distance, how much elevation incline do we want, and it will figure that out based on all of the different parameters that we've put in there. And we get what's called a convergence, and this is where the Bellman equation really comes in with optimizing everything of, once we've discovered everything about our environment, we can then go about exploiting it and figuring out what is our best way to do that. Now, what is to stop the algorithm from just going back and forth and receiving its rewards infinitely? We use what's called an epsilon greedy. I'm not going to go through the math of it because there isn't really a whole lot of math to it. It's basically a value that you set with a certain degrade rate, and it randomly chooses whether the algorithm is going to go try to explore something new or whether it's going to go back exploiting how it does. So a simple example of this is when we talk about optimizations with learning rate and discount rate. Do we want a situation where we're trying to get to an ultimate goal, or do we want a situation where you're playing the board game Clue and you just keep going back and forth into the conservatory and out of the conservatory so you can ask everybody every single question that you need to know and then proceed straight to the end result and guess? Depending on what problem you have, you might want to go that route, or you might, in the case of our hiking one, I don't necessarily want to be going in a whole bunch of circles to get to the top of our hill. I want the hill to be kind of the end result for our maximum piece. So let's talk about this learning rate, discount rate that I've been talking about. What are they? How do they affect our decision-making processes? So the learning rate is the memory span of the algorithm. It's the easiest way to think about this. So the closer to 0 that learning rate is, the more the new Q score is going to rewrite the old Q score. So remember that when it's going through, it's trying to figure out every single possible combination of actions and rewards, and it's going to rewrite the Q table. How much of those old scores we want to stay is going to be determined by this learning rate. So in some circumstances, we might want a really long learning rate. Going through the same space on a hike is not going to be helpful, versus jumping up and down in a Mario game where we continue to get coins and a reward over and over and over again. We might want a shorter learning rate for that second example, so that we keep doing the same action over and over and over again and looping through that space if we keep getting that gratification. Obviously not ideal for a hike. The second piece is the discount rate. I like to think of this as the addiction rate. It's the best way I can describe it, of how quickly does your algorithm need to get another hit of that reward. It doesn't matter what size the reward is, even if it's small, it needs to keep getting that reward status over and over and over again. Otherwise, it's going to think it's failing. So this is, if you were to set the discount rate to 0, it needs that immediate hit over and over and over again. So think of our clue game of going in and out of the conservatory over and over and over again, so that it keeps getting that reward of more information. And it'll keep doing that until it exploits it and it doesn't get that reward anymore. In our hiking example, when we're trying to get to the top of the hill, we would want a discount rate closer to 1, because we want that eventual gratification of hitting the top of the hill. We less care about the small successes of, did I go down 5 feet in elevation over and over and over again? Was this continually a shorter distance? The end goal is more important than the immediate gratification. So by tweaking the learning rate and the discount rate, you can solve for things that you need more short-term goals for, or more long-term goals. And then the final optimization that you can look at is the cutoff point. And this all needs to be taken into a thought process of how we want to deal with our long-term or short-term goals. The following is my works cited. If you liked this presentation and want to try it out for yourself, I highly recommend looking at Deep Lizard. They have a great thing on how to code a reinforcement Q-learning model against old Atari games, so I highly recommend checking it out. Thank you so much, and have a great day.